Welcome to the last Chapter 9 lecture. Let's go ahead and get started. This will be dealing with reactions of ethers. This is section 9.14. Reactions of ethers with strong acids is the first thing we're going to do. Very similar to alcohols. Let's look at an ether. HBr excess, or two equivalents. We're going to need two equivalents for this. We're going to get two different bromides. Two different alkyl bromides. And we're going to get two equivalents of water. I'll show that. So let's add HBr. Protonation. Get dissociation. Now, this is actually an interesting question as to the order of events here, because you're going to form a bromine-carbon bond in both cases. I would argue that the bromine is a weak nucleophile, weak but effective, and so if you have a chance to form a carbocation, then go ahead and form it. And then Br minus can capture that. That gives you one product. Now, what was the byproduct? Methanol. Now, we've already seen this. This is a combination of mechanisms. We've already seen this mechanism. If you add HBr to methanol, what do you get? Dissociation. And now the only option is SN2. Attacks the carbon, kicks out water. You get this product, and you get water. So actually you only get one equivalent of water. I said two equivalents, but you get one equivalent. Makes more sense. Okay? So you convert an ether to two different alkyl bromides, sort of similar to the mechanisms we've been talking about. So you could look at some of these problems. You could have a secondary. Ethers are made up of two different carbon-oxygen bonds, so that's a secondary, and that's a primary or a special primary. It's a methyl. You add HI excess. What do you get? You get the secondary iodide, and you get the methyl iodide. There's a molecule of water. Same idea. Secondary, actual primary, HBr excess. You can fill those in. This is an interesting case here. HBr excess. You'll get the methyl bromide from this part here, but you'll end up getting this as a leaving group, and then you probably will get protonation from the excess HBr. So you'd end up with a dissociated form of what's called a phenol. right, the Br minus is not going to attack this sp2 hybridized carbon. So that's reactions of ethers with strong acids. We can look at 9.15, and that is thiols and sulfides, and this is just sulfur-containing sulfur analogs of alcohols. Okay, so let's just do naming really quickly. For naming, in general, we're doing linear naming only with no substituents. We're going to keep this pretty simple. So I want you to learn the names of the first 8. Methane thiol. All the way down to octane thiol. It's just the sulfur version of an alcohol. Sulfur version of an ether, we're only doing symmetricals. Symmetrical only. Which means 2 methyl groups. Dimethyl sulfide. All the way down to dioctyl sulfide. That's all we're doing for naming of sulfur. Okay, linear only for the thiols, and linear and symmetrical only for sulfides, the sulfur versions of alcohols and ethers. Let's look at 2 reactions. You can recall from chapter 7. This is recall that you can take an alkyl bromide and treat it with Na plus SN2 reaction. Right? This negatively charged sulfur does just what an oxygen would do, and you get this product. You can make these types of products by using sodium hydride, like we showed with alcohols. You can deprotonate with this strong base and generate this negatively charged sulfur that can react with CH3I, and now you make the same product by the opposite direction. Okay, and not a lot on sulfur, but we should be able to use sulfur nucleophiles. All right, let's look at 9.16. This is reactions of epoxides. Epoxides are very important because they have ring strain. These are ethers, so this is more reactions of ethers, but they're special cyclic ethers. Okay. And we want to look at these. Let's start with a simple epoxide. The simplest epoxide is called ethylene oxide. It's the oxide of ethylene. Okay. Ethylene is the simplest alkene. It's a very useful molecule. Okay. There's lots of things you can do. Let's show a few. You can treat with sodium cyanide. This little I means that this is a sequential reaction in the same flask. Little I, double little I. And you can quench this with water. Okay. This is the product. You actually get inversion here. It's irrelevant right now because you have two H's, but we'll see cases where you have two stereo, or have a stereo center and you get inversion. Okay, so let's go over a mechanism. You have this cyanide, and again, general rules, we said that localized oxygen negative charges are going to be strong bases. Other than that, we're going to treat them as nucleophiles. So we've never treated this as a base. Okay, so we're going to treat it as a nucleophile. That's going to open up the epoxide. That's SN2. And so it's attacking from the backside. And imagine this oxygen is like a leaving group. It's not leaving the whole molecule, but it is leaving that carbon. Okay? Because of the ring strain, that oxygen becomes functionally a leaving group at that carbon. And it's left over right here. So then you have a negative charge there. What can happen next? We have excess water. Water and alcohols have a similar pKa, so this H is about the same acidity as this, but if we have excess, it can drive that equilibrium. We can use water to quench a reaction. You might use acid, okay? Acid might be more practical, but we can use water. And then what's left over, there was sodium here. What's left over is sodium hydroxide, okay, as our byproduct. That's one reaction of epoxides. The other one is with acid. That was with base. We add HCl to this. We get a similar looking product. Let's look at this mechanism. Same idea. You have an ether and a strong acid that's going to protonate the ether. In this case, it's a cyclic ether. It's epoxide. So now we have a dissociated HCl. That's protonation. Now, this polarized bond, we had a partial plus and a partial minus. Okay. Now, even though there's a plus charge on oxygen, this makes this partial plus even more partial plus. But it doesn't form a carbocation because there's a bond there. And there's ring strain. The chlorine now, because of the ring strain, the chlorine can come in and attack in an SN2-like reaction. Let's put the arrow this way. Pops it open. There's an H here. Pops it open. SN2. Inversion. Okay, there's always inversion with SN2. So in reality, we could draw it like this. Backside attack. This is our leaving group. And this goes up to product. That's it. Okay. So protonation, SN2 inversion. Now, ring strain facilitates, let's put it this way, facilitates inversion. Inversion. Because of the ring strain inherent to epoxides, that chloride isn't any better nucleophile than it has been, but it's the ring strain, it's going to be able to come in there in a concerted way and pop it open. All right, so that's the simplest epoxide. It's symmetrical. What if we have one that is unsymmetrical? Two-step process, sodium methoxide followed by excess water. It's going to give regioselectivity. It's going to attack one carbon. One single carbon, not both. Let's show that mechanistically. Backside attack pops this open. Again, think of this as like a primary tosylate is a good way to think about it. Primary O-tosyl or primary bromide. If that was an O-tosyl, right, carbon, CH2O, and a leaving group, this is a primary, SN2. Pop that open, ring strain, even better, and so you get the sodium alkoxide. This is attacking at the less sterically hindered carbon. All right, it did not attack here because it's a tertiary-like carbon. It attacked at the primary-like carbon. It popped it open. Basic conditions will attack at the less hindered carbon. Okay. Now we can add water. Again, excess water helps drive this. You could add acid. You get sodium hydroxide as your byproduct, and you get your product. Let's do another couple reactions. Let's do another single enantiomer, or let's do one that's a single enantiomer. That is unsymmetrical. You can put in the lone pairs, step 1, step 2. Again, this means it's all in the same flask. So we add this for a period of time, let it do its magic, and then we add the water, and we get out this product. Only. Notice the H is on the opposite side of the molecule. That's what we mean by inversion. Okay. So this center is inverted. Right there, that stereo center is inverted. Single enantiomer in, single enantiomer out. You can go through that mechanism. It's SN2. That O- is attacking this stereo center, popping it open, giving inversion. Came from the back side, so the H is now in the front over here, as opposed to the back. What happens if we add the same kinds of reagents to a meso epoxide? There's a plane of symmetry here, so this is a meso. We add exactly the same conditions. What do we get? We get a pair of stereoisomers. Okay, that's CH3O- can attack at either carbon. There or there. SN2 in both cases, protonation. Gives 2 trans alcohols. They're both trans, but they are enantiomers. It's a racemic mixture. Okay. work on those mechanisms. Okay, so we just established that a basic reagent, a basic nucleophile, a negatively charged nucleophile, will attack at the less hindered carbon. So that's basic conditions. What happens if we have an unsymmetrical epoxide? Sorry, wedges and dashes. Unsymmetrical epoxide with acid. Okay, we showed HCl before. Now, under acidic conditions, you're actually going to get reaction over here with this carbon. We'll go over this mechanism. This is a very, very interesting mechanism. You only get this product. We're going to look at one with a stereocenter. We're going to get a single enantiomer. We'll show that in a second. Let's go over this mechanism first. What happens with HCl? Same first step. Cl minus. What can happen? It could attack over here, but it doesn't. Okay, there's a reason for this. It's very interesting what happens. Basic conditions, because we've protonated this oxygen, okay, we have increased the partial positive character of this carbon, but it doesn't form a carbocation. This doesn't just break and form a carbocation, okay, and it doesn't attack here, but it attacks the more partially positive carbon, okay, the more electrophilic carbon, and pops it open, but it does so in a concerted way. So it's SN2-like in that it gives inversion, but it's SN1-like in that it attacks more positive carbon, but not a carbocation. It's really fascinating. It's a hybrid between SN2 and SN1. Okay, that leads us to product right there, and you only get inversion. Now, there's no stereochemistry here, so it doesn't matter, but we're going to show a case where it does matter. Okay. Before we do that, well, let's do that. It's important to follow up now. So let's show a single enantiomer epoxide with HBr this time, in which you get a single enantiomer of the bromine attacking at the more substituted carbon. Again, SN2-like in that it's inversion, SN1-like in that it attacks the more substituted carbon. Okay, the ring strain of epoxides allows this really unique reaction system. Okay, so it's not a true SN2 because a true SN2 is too sterically hindered, but because of the ring strain, this Br minus can come in and do inversion. It's really kind of fascinating. There's some nice illustrations of this in the text. If you want to look at it a little deeper, they show some potential transition states of chapter 9. Yeah, figure 9.10. Gives some transition states and talks about the more stable transition state, and that's why you get it the more substituted. Okay. When there's a single enantiomer, this becomes very important. Okay. Again, you're going to protonate that epoxide, and then the Br minus will come in here and attack after protonation. So we can kind of abbreviate the mechanism. We'll come in and do SN2 inversion. Okay. Let's show another set of conditions. You can take an epoxide and do two things here. You can add H2SO4, strong acid, and water, excess, aqueous sulfuric acid. You're going to get two enantiomers. You get a trans diol. This is on page 369. You can see that. Okay. We can go over a mechanism in class. Basically, you get H3O+. H3O+ is going to protonate the epoxide, and then water is going to come in. It's a steppy mechanism, so we'll save that for class. Then you can add H2SO4 with methanol. Same idea, but now it's methanol. You get two enantiomers of this trans product. Okay, you can do the exact same reaction with PTSA, para-toluene sulfonic acid, with methanol or ethanol or whatever. We'll go over some of this in class, and you get the same products if it's methanol again. Okay, so look into that a little bit. Finally, you can use an amine. Okay. So this is the one problem with rules is you give rules or guidelines, and then there are exceptions. But again, it's the ring strain that's causing this exception. Draw the epoxide a little differently than we've been drawing it. We've been putting it in the plane. Now we can kind of put it out of the plane, so to speak. You can put the H down here like that. So you can draw it differently. Now the epoxide's kind of back. And you can add an amine. So let's put H2 there. You get phenyl. It's a really practical way to make amino alcohols. Okay, let's do a mechanism. Again, we said amines of this type, neutral amines, not DBU or DBN, and not negatively charged amines. We said these are moderate bases and moderate nucleophiles, and so these can open up. They're not going to act as a base. There's no real protons to deprotonate here. They're not going to act as a base. It's going to act as a nucleophile. Sorry, that's an arrow. Popping that open. What do we have? Initially, we have the protonated nitrogen, but we can go 1, 2, 3, 4, 5. We can, in this case, we can show a intramolecular deprotonation. The O- is a better base. It's going to pick up the proton here and give product. Okay, if we compare pKa's, just do a pK of about 11. pK of an alcohol is about 16. Okay, so this is a better acid. And you get to the amino alcohol. Okay. 9.17, 9.18 are applications. Very interesting. You should read through. And but that's where we'll end the lecture. And that ends chapter 9. We'll see you in class on Monday.